All right, thank you very much for your patience. Let's get started. This is 2023 test 2. And in this part, we'll do the first two questions. They are long. Okay, the first question here. Give the structures for compounds A up to E in the synthetic scheme below. Want to give the structures of the compounds from A to the compound E. Now, if we can see, we are starting with cyclohexano. And this is just what we have been revising for some few days ago. So this is an alcohol, right? So please, if you know as a way of revision, be able to comment so that you do revise. So this is an alcohol. I can put the OH functional group here. When you react an alcohol, there is a mic that is on. Please let's switch it off. If we want to speak now, turn it on. When you react an alcohol with an acid, what are we supposed to produce? As a way of revising. Pardon? Can you say that again? I didn't get you. Docs, we have done this before. Let's get to speak. Okay, so this one we get a carbonyl group. So when you are reacting an alcohol with sulfuric acid, you can get an alkene. But then this one we are using here is an oxidizing agent. And what we have is a secondary alcohol. So secondary alcohols will be converted to ketones. Primary alcohols will be converted to carboxylic acids. If you are using a weak oxidizing agent like PCC, we convert primary alcohols to aldehydes. Now we are getting A, which is a ketone. We are reacting it with a Grignard reagent. What is the product that we're expecting? Anyone? So the Grignard reagent to be able to convert a carbonyl group into an alcohol. Look at this. The first thing that happens is that this CH3, which we can see here, okay. I hope you are able to see it. So it's like this CH3 MgBr, like that. This thing can just move away. So it becomes CH3 with a minus because it gains the two electrons. This one will act as a nucleophile which will come and attack this end. When it attacks, this bond breaks off. When that bond breaks off, it will now go and grab a hydrogen. You can see the second reactant is protonated water. From protonated water to be able to remove a hydrogen. And then you get to form your alcohol. But remember, you had the attachment of your methyl. The methyl was first attacking. So the methyl had to attack. And then we also formed our OH. So this is going to be the structure B. Now when you react an alcohol, look at this. Now this is where the doc had mentioned earlier. You can please mention what you mentioned earlier. When you react this alcohol with this acid, what are we going to form? We'll form an alkene, yes. So when you use an acid, for example, sulfuric acid, you eat the solution, you form an alkene from an alcohol. Okay, what will happen is that this oxygen will grab that H, which is, you can see they've just given a general form of an acid HA, to grab this hydrogen this bond breaks off, we are going to form protonated water like with two hydrogens to the positive. And then what happens is that this group can leave, and then we can come and grab a proton at any one carbon, one step away from this carbon. We can grab from this carbon, can also grab from this carbon. So that is what happens. So now we have formed our alkene, that is C. Then now we can see that this alkene, we are reacting it with ozone and dimethyl sulfide. What does ozone do? Anyone? So ozone, in what is known as ozonolysis, will be able to break this double bond on the middle. So break that double bond on the middle, and then the structure we're going to have is something like this. Okay, like that. Simply attach an oxygen at this end and simply attach another oxygen at the other end. So this will be our product. This is D. Now we just want to write it in a good way, So let's number the carbons: 1, 2, 3, 4, 5, 6, and 7. So I can write that 7 carbons: 1, 2, 3, 4, 5, 6, 7. At this end, we have got a double bond at position number 6. Position number 1 also have a double bond with oxygen. Is this okay? Please be free to ask. Is this okay? Okay, when you use an acid and heat, you are going to be able to you are going to be able to convert an alcohol. So what happens is this: alcohol, when you use an acid, say sulfuric acid, and water with heat, you convert it to an alkene. This reaction can go back. Okay, it just depends with which one is more in concentration. So if you have got more water than acid, you convert an alkene to an alcohol. When you have got more acid than water, you convert an alcohol to an alkene. It goes in a reverse direction. That requires heat. That is because if you do not heat, you are going to get other products which is not what we want. I don't know if that's okay. Is that okay? Okay, thank you. And then in the next one, you can see we are converting D. Now we are converting it to E. Look at what we are reacting with. The reagent we are using here is known as Tholen's reagent. Anyone please to help us? If you are having Tholen's reagent and then you have got what does Tholen's reagent do? So Tholen's reagent, anyone who can help us? Okay, here we'll simply convert the functional group of of an aldehyde to the carboxylic acid. Now, an aldehyde is always the double bond with oxygen at the end of a chain. You are converting it to a carboxylic acid, so simply attach OH here. And that's how you do it. Simply attach OH at the end. So this is our E. Are we good with all the steps here? So when you use this reagent, silver, ammonium hydroxide, Tholen's reagent, convert a carboxylic acid. You convert an aldehyde into a carboxylic acid. Aldehyde functional group is the OH, the double bond with oxygen. at the end of the chain. This other one which is here is ketone because the double bond with oxygen is on the middle of the chain. That's okay? Okay, thank you. Let's look at this one. A compound of formula C5H10O gave a positive reaction with Brady's reagent, gave a negative reaction with Fehling solution. Is that a question, Doc? On okay. So we had an alcohol. We are converting it to a carbonyl group, which is a ketone. So what should we know? What we need to know is that when we have got primary alcohols can be converted into aldehydes. Okay, aldehydes, and then these ones also can be converted into carboxylic acids. And then when you have got a secondary alcohol can be converted into a ketone. And here we use oxidizing agents. Oxidizing agents that we are able to use in this reaction. For me to convert a primary alcohol into an aldehyde, I should use PCC. Okay. But if I want to convert a primary alcohol into a carboxylic acid, I can use potassium permanganate, and then I can use also this compound K2CR2O7. C is potassium, should be perchlorate. I don't know the name of. Okay. So these guys are strong oxidizing agents. If I use either PCC, potassium permanganate, potassium perchlorate, sometimes you'll see they've not used potassium, they've used sodium in front there. These two don't affect anything. Whether it's sodium perchlorate, potassium perchlorate, don't get confused. So if I use any one of these three for primary alcohols, they will still convert primary alcohols into a ketone. And the alcohol we have here is a secondary alcohol, not primary. The alcohol that we've been given in this question is a secondary alcohol, if you can see. So that is why this alcohol is being converted into a ketone because it is secondary. Is that okay? Okay, so thank you. So take note that tertiary alcohols do not undergo oxidation because they do not have an alpha hydrogen. A compound of formula, the formula I've been given is C5H10O, gave a positive reaction with Brady's reagent. Now, here we have got positive Brady. Anyone to help us? If you have got a positive Brady's reagent, what does that give? What does that mean? What do we have? Anyone? I don't know if we are forgetting or if we don't want to answer, but if we don't want if we don't just want to answer, that's bad. If we are forgetting, that's also bad. We need to go to check through. Okay, so I'll write again the tests. Okay, thank you very much. So write the test and then we'll write what it does for aldehydes, what it does for ketones, and then the color we expect. So starting with the Brady's test, Now in the Brady's test, this reagent is 2,4 dinitrophenylhydrazine. This test detects carbonyl groups. As long as a compound has got a double bond with oxygen, a carbonyl group, it will be positive. So meaning it is positive for both aldehydes and ketones. And the color that you see like will be yellow to orange. That will be a solid, a precipitate. We also have the tolerance test or tolerance reagent. Now the tolerance reagent will basically use silver, some sodium hydroxide. Okay, we saw it earlier on the previous question, ammonium. So every time you see silver, something has been reacted to silver like that, just know that's the tolerance reagent. This one will give a positive test for aldehydes, but it will give a negative test for ketones. Okay, and the color that you are going to be able to see is not actually a color, but a silver mirror if the aldehyde is there. We also have the Felling's test. Felling's test, for this one, we use a solution of copper and sodium hydroxide and those other things. It's also positive for aldehydes, negative for ketones. The color it gives is a red precipitate. We also have the iodoform test. Now for the iodoform test, this one, what you basically use is the iodine, is sodium iodine and some sodium hydroxide in there. This one is not detected and is not detecting any functional group as aldehyde or ketone. It just detects the presence of a terminal methyl group. Please, it's terminal, not just any methyl group, but terminal methyl. So if you get a positive reaction here, the color you are going to be able to see is going to be a yellow precipitate or a yellow solid. Okay, so now we can answer our question. In here we had a positive Brady. That means that we have got a carbonyl group. The other thing that we had was it gave a negative reaction with Fellings. That means it wasn't an aldehyde, meaning it is a ketone. Gave a yellow pipette with when treated with 10% iodine, potassium iodine. So that means that is having a terminal methyl because that is an iodoform test. That's the terminal methyl group. So draw the structures of all the compounds that would give these results. Okay. So one thing, remember the formula is C5H10O. If you are not even sure if you are going to have a lot of double bonds in this molecule, you can also find the IHD. IHD is given by 2 times carbon, so I've got 5 carbons plus 2 minus I've got 10 hydrogens over 2. This is giving us IHD of 1. Meaning that for this one, since we are only going to have one double bond, only one double bond, that's the meaning of 1 HD. It would have also meant we could have one ring, but if we have got a ring, then it means we will not have any double bond. But since we are having a ketone, definitely we should have a double bond because for us to form a ketone, we need a double bond with oxygen. So meaning that there's no possibility of having a ring for this structure. So 5 carbons, I can write 1, 2, 3, 4, 5. At the end, I need to have a terminal methyl, so the double bond, I'll put it here. I can write another one like so. This is 3 carbons, 1, 2, 3. The fourth one, I can write it here. The fifth one, I can write it here. So these are the possible structures that I'm able to draw for this one. Okay. I can't divert any more apart from this. Is this okay? Are we good? We can't have a ring because for us to form a ketone, we need a double bond. So meaning that this one IHD is already cut by the double bond that we are forming with the oxygen. So that's why we cannot have a ring. When the following compounds are mixed, an acid-base reaction is expected. Predict the products of such a reaction in each case. So you can see we've been given that the pKa for water. So let's start with the first reaction. We have been given CH3, NH2 reacting with water. We need to use their pKa's. The pKa for water is 15.7. For the other one is 30. So which one is the stronger acid between these two guys? Which one? Thank you very much. So the lower the pKa, the stronger the acid. The one which is a stronger acid would donate a proton because acids are proton donors. So the CH3 NH will gain another hydrogen, so it becomes 3. Every time a compound gains an hydrogen, it becomes positive charge. So the nitrogen will become positively charged. Water has lost the hydrogen, so it will remain negatively charged. For the other one, I don't know if we have understood the question on top. All right, thank you. So now let's look at the one down. We have got phosphine and the H2S. Now remember what we said. When you are comparing atoms going down the period, when you want to go, all right. Okay, so for the first one, we are given the pKa for both water and the other reactant. The other one is 30, the other one is 15.7. So we said the lower the pKa, the stronger the acid. And acids are proton donors. So what water will do is that it will donate a proton to the other compound. So it had two protons, there will now be three. So when something gains an extra proton, it will become positively charged. Then the water will become negative because it has lost the hydrogen, so it's now hydroxide. Is that okay? Okay, and then the next one we have got pH3 plus CH2S. So I was saying if you compare atoms in the same group, let's say for example group 7, we have got fluorine, we have got chlorine, got bromine, we have got iodide. If these form acids by just attaching H in front, the strength of the acid you use size. So as you go down, because atoms are becoming bigger, they could be more stronger as acids. When they lose these hydrogens, as you go up, basicity to increase. So when acids lose hydrogen, they become bases. So the strongest base is going to be from F because it is the weakest acid. When you are comparing atoms which are in the same period from left to right, you use electronegativity and not size. All right. So for example, in the periodic table I've got carbon, nitrogen, oxygen, phosphorus, and then down nitrogen, phosphorus, sulfur, chlorine. So you can see these two guys. For me to compare phosphorus and sulfur, I can't use this size. Instead, I'll use the electronegativity. Okay. So here we can see sulfur is going to be more electronegative because it is much closer to fluorine. The closer an atom is to fluorine, the more electronegative it is. And a strength of acids as you go from left to right will increase. So sulfur will form stronger acids than phosphorus. So in this reaction, sulfur will be the one to donate a proton. So it will become 4. Yes, please. They're more acidic when you are comparing from left to right, yes, but not from up to down. So when you are comparing from up to down, you don't use electronegativity as a property to talk about strength, but you use size. The stronger, the stronger an acid it can form, yes. That's okay? Okay. Let's look at this one. Consider the following molecule. Now they just said resonance. Okay, they said write the resonance structure for this one. Now this structure is, look at this. It has got one electron. We call a compound that has got an odd number of electrons as a radical. So this is a radical. Now resonance of a radical is different from resonance of a carbocation. Let's say if this was a carbocation, like so. When you want to show resonance, you just move this double bond to here. Resonance you always show using a double arrow like that. So double bond would have come here, the positive charge would have come here. That's how you show resonance for carbocations. Different from resonance for radicals. For radicals, this one electron will move. When you are moving one electron, you use an arrow like this. Look at this, it's an half arrow. It's an half arrow. Let me write it properly. Never write a full arrow, please. You are showing an half arrow like so. Now from this double bond, remember a double bond has got two electrons. So one electron will move from here, it also come here. The other electron is going to go at the end. Okay, so that is how you show resonance for a radical. So this is what you are going to end up with. Because you have now two electrons together here, they are going to form a new bond. So that will be our double bond at this point. And then remember you have got this electron which has gone at the end, so that comes here. So this is going to be our resonance. It's all about arrows. If you miss the arrows, then you miss the 2 marks. Is that okay? Okay. The next one is saying extended pi orbital overlap, delocalization. Want to explain the extended pi orbital overlap or delocalization to account for the extraordinary stability of the allylic type radical. Now this is a primary radical. Why is it that it is very much stable? Why is it a very stable radical? So using the extended pi orbital, that's pi, that's to do with the double bond. So look at this. If you look at this carbon here, how many things is it bonded to? This carbon here. Okay, let's look at the atoms it's bonded to. The first atom I know is this one here. Which other atoms is it bonded to? Which? Yes, how many hydrogens? There are two hydrogens. So this carbon is bonded to three things. The carbon is bonded to three things. It has got sp2 hybridization. If it was bonded to four things, sp3. If it's bonded to two things, it is sp. This carbon here is only bonded to how many things? Three things. It's also bonded to three things. Let's see. A bond here, a bond here. So like one thing this side, one thing this side. There's also a hidden hydrogen. So it is also sp2 hybridized. That is what I want us to understand there. So and is also sp2 hybridized. So let me write these two carbons. So this is a carbon. It has got sp2 hybridizations, and they are going to be the three of them. Look at this. You have got S, you have got a P, you have got a P. Yes, please. So it has got a one bond, two bonds, three bonds, and the carbon should always have four bonds. So meaning that the fourth bond is a hydrogen. Yes. So we are saying this is sp3 hybridization. So what that means is that we have got three orbitals, okay, which are sp3 hybridized. Now these are hybrid orbitals. What do you mean by hybrid orbitals? Hybrid orbitals means that these orbitals are formed by a combination of more than one orbital. You can see we have got the s orbital and the p orbital. So I'm going to write these ones. I've got one, I've got two, and then I've got three. These are representing sp2 orbitals. There are the three of them. Now, if I've got a compound that is sp2 hybridized, it means that it has got one p orbital that is not hybridized. And the p orbital looks like this. It looks like so, like infinity. So if this compound was sp hybridized, it means that I would have had two of these guys. So this is one carbon, the first carbon that we have written here. This is the first carbon. And then there's going to be another carbon, which is this carbon here. It also has the same hybridization. So it's going to have one orbital like this, which will overlap with the other one. Another orbital like that. Another orbital like this. Okay. So these are all the ones I'm writing in pink. These are sp2 hybridized. And then we have got also a p orbital. P is not hybridized. This one is an atomic orbital. It's not an hybrid orbital. So what actually happens is that we are going to have one electron in this one sp2 orbital from one compound, and then the other electron is coming from the other compound. They are facing in opposite directions. That forms a bond, and we call this as a sigma bond. The sigma bond is formed by parallel head-on collision. You can see these are hitting each other. But then in this p orbital, I'm going to have one electron. In this p orbital here, I also have one electron. Now, because for this carbon, which is this side, this carbon, it has got two hydrogens. It's going to have one hydrogen here. That hydrogen brings this one electron. The other orbital here also brings one electron to form a bond. This one also bring one electron from the hydrogen, one electron from the carbon. This carbon, which is at this point, has got only one hydrogen. That one hydrogen brings this electron. The other electron is coming from the carbon. But remember, it is also this carbon here is also bonded to another carbon which is here. So it will be bonded to a carbon this side. Okay. Now, these p orbitals, what can happen is that they can actually overlap on top and down. So that parallel overlap, you can see this overlap here is parallel. That parallel overlap is going to result in the formation of a pi bond. And that is what accounts for the double bond that we are able to see. And that pi bond is able to stabilize the molecule because there's going to be possibility of resonance because of that double pi bond. Because remember, this is supposed to be a carbon, but this carbon is bonded again to other things. It also has a hybridization. But this one is going to be bonded to how many things? Four things. So this one is going to be sp3 hybridized. So it's going to have three other hybrid orbitals where hydrogens are going to be bound. So there's a possibility of these pi bonds forming resonance by changing between this carbon 1, this carbon 2, and between carbon 2 and carbon 3. That is what explains the stability that has to do with the pi orbital overlap. The formation of a pi bond here stabilizes the molecule further and maketh possible a formation of a pi bond that can form resonance to stabilize the molecule. I've tried. I don't know if I could have done better than that. I don't know. Is that okay? If you can remember it, you can draw it, but I can see they didn't mark the structure, just marked the statement. So you can use the statement if you can remember. Okay, so we have got this question now. Predict a major product F and G, give the name of each reaction, and provide the mechanism for the formation of each product. Now we are starting with benzene. We have got benzene. I love these reactions for benzenes. There should be just 5 of them. There is nitration, there is Friedel-Crafts alkylation, Friedel-Crafts acylation, which other one? Halogenation. The other one I've forgotten the name. So just about 5. So when you are reacting with nitric acid in the presence of sulfuric acid, this is called nitration. You need to know that the product that you're expecting here, let me do this. I think it will really, really, really help a lot. Let me just write the general ones so that we can see if it comes in any way, we'll not be able to fail that one. Okay. Instead of, because at this point, if we just be mastering, okay, this one is this one, this one is this one, I don't think that would be able to help. So the first reaction is going to be a nitration, and what we are reacting with is basically, sorry for that. Let me write benzene on the middle. Please take note of these. Okay. Help me just to write the names. I might not be able to write the names. So, okay, let me just write halogenation. Let me not be lazy to write halogenation. There is a Friedel Craft acylation. There is Friedel Craft alkylation. And then we also have, which other one did I even mention earlier? Halogenation, Friedel Crafts. Okay, there's nitration. And then the other one is going to be sulfonation. Now, what is important is what reagent should you see? Okay, so for halogenation, what you are going to do is you are going to react an halogen. Can be bromine, it can be chlorine. But then you are going to see you also use ion. Whatsoever halogen that you are going to use, you see it like that. Ion with X3. So if X is chlorine, you are going to have chlorine with a 3. If it's bromine, bromine with a 3. And what should be the product that you are expecting here? The product that you're expecting is that you are going to attach your halogen to the ring. Okay, that is going to be X there. In Friedel-Crafts, let's start with nitration. Nitration what you are going to use is nitric oxide. Sorry, not nitric oxide, but nitric acid. You also use this sulfuric acid. This is good. You can form the same product without sulfuric acid, but then it's going to be slow. So here what you are basically adding is nitrogen oxide to your compound. That's when you see these reactants. Okay. And then you have got the Friedels. So Friedel-Crafts alkylation and acylation. Now, alkylation just means that you're adding an alkyl group, that is an ara group, to your benzene ring. Okay. So even in the reactant, you are going to see an ara group. For the acylation, you're adding an acyl group. An acyl group is this group. An acyl group is a group with a double bond to oxygen like that. And then you can have a chlorine here, and then you have got ara group here. So what you are going to be able to see is that you are going to see the chlorine being removed. Okay, and then you just attach to your chain something like this, and then double bond to oxygen, and then with your R group there. If you see this product, that is acylation. And then sulfonation, what you'll be able to see is you are going to see SO3, and then there's an hydrogen. If I write it like this, it will mean something else. It will mean that the hydrogen is the one having a 3. Let me write it like so, SO3H. So these are the things that you'll be able to see. For the sulfonation, we're going to see sulfur trioxide being used with sulfuric acid. It is the same as nitration. The only difference is that you are seeing sulfur trioxide and then sulfuric acid. For the Friedel-Crafts acylation, here we're going to use an acyl group with aluminum chloride, and then the alkylation, we have got the alkyl group. Now the alkyl group is always bonded to R. Okay. Acylation, you just see Ara with an alkyl group. An alkyl group is just bonded to oxygen and then with a chlorine at the end. You always use aluminum chloride here. And then for alkylation, you have got an alkyl Ara with a Cl. And then it is also having aluminum chloride. So these are the reactions that you need to know about benzenes: sulfonation, halogenation, Friedel-Crafts acylation, Friedel-Crafts alkylation, nitration. Please take note of the products that you expect at the end. Can I remove this? Now we look at the mechanisms. Should I remove? Okay. So the mechanisms are the same. So if you understand the mechanism for these two, then you are going to understand the mechanism for the rest. If you want to know the rest, go in our playlist, just in the group description. I've just opened it for everyone in the group description, and it's only open for us here, so it's not to be gotten and then being sent somewhere else. So you can open it and then go where it is written aromatic hydrocarbons or benzene, something like that, and watch the others. Okay, let's start with the formation of F. So the formation of F, you can see what in the first step you always start. Please always start with your reactants for all of these. The mic which is on, please kindly switch it off. So I'm going to start with your reactants. So these are our two reactants. But then I can't do a mechanism like this. How do they mark me a mechanism like that? I need to write the structures. So I've got, remember, every time you see CO, that is a carbon double bonded to oxygen. But you have got two carbons. So carbon number 1, carbon number 2. Double bonded to oxygen. And then we have got a chlorine at the end. And then I've got aluminum trichloride. Something like this. Now, in this mechanism, the chlorine will be the one which will be acting as a nucleophile. This chlorine can come and attack here. There is nothing that will be able to live on the aluminum chloride as the other mechanism that you've known. So this is a different topic. So the chlorine will be like that. It's bonded to aluminum, okay? And then aluminum, remember, has got 3 chlorines. Because chlorine has bound there, is going to have a positive charge. Don't forget that. Aluminum will now carry a negative charge because it has got too many bonds. In the next step, what is going to happen is that will be step 2. In step 2, this bond will be able to break. So the aim, actually the mechanism of this is we want to form something that is positive, because the ring will be able to attack. It is a nucleophile. So a nucleophile attacks an electrophile. Electrophiles are negatively charged. So when this breaks, the product we are going to see is going to be like so. So it's going to be positively charged. And then we are going to remove the aluminium with 4 chlorines, the fourth one being this one. Aluminium is negatively charged, don't forget that. Okay, in the next step, that is going to be step 3, because the step 2 has to do with this one here. The benzene ring now comes in. Don't forget it has alternating bonds inside. It is attacking an electrophile. Electrophile is something with positive charge. So I've just written it in the opposite direction. This double bond will come and attack this. When the double bond attacks that, what you're able to see is that it will come. So this double bond is still there, this double bond is still there. This group will come and attach here. Now when that group attaches at that point, double bond in the ring will break, so we're going to have a positive charge at that point. That positive charge has to be stabilized. Now, let me mention this. I've never mentioned it. Don't take a lot of time writing. Take a lot of time listening, because the tutorial will still be available for you to write again. But understanding now, for you to be able to ask, you have little time to do that. So are we good up to this end? Are we good up to here? Okay, at this end that we have reached, this molecule is going to be stabilized by resonance. So we are going to have different resonance structures. So we'll be showing resonance now. If you leave out the resonance, you lose some marks. So this double bond can move up to here. The stress that we are going to have now, I've got a double bond here, a double bond here. Every time a double bond moves, the positive charge will jump one carbon, so it will come here where it is empty. Then again, this double bond can move up to here. That will be another resonance structure. So there's a double bond here, there's a double bond here. So the positive charge will again jump one carbon, it will now come here. So these are these are the 3 resonance structures that we are going to have for this molecule. And that is why when benzene rings form carbocations, they are very much stable because of resonance. At this point where we've reached now, I'm going to just get the first structure which I had formed. A double bond here and a double bond here. There was a positive charge at this point. Now remember, in the reaction we had formed this Cl, which was bonded to aluminium. This aluminium had the 3 chlorines, and this one we said it was negatively charged. Don't forget this one. Okay, so what will happen is that now this one will come in. I've written it even too far. This is Cl bonded to aluminium, bonded to chlorine with a negative charge. This chlorine has got lone pairs. What will happen is that this bond will start to break off, and then this chlorine will come and act as a nucleophile, attacking where the positive charge is. So in the process, we are releasing aluminium chloride. And then now what we are forming is this. Oh, sorry, I've actually gone to do something that is wrong. We are not attacking. I don't know what came over me. We're not attacking. So what we do is we want to form the double bond that was broken. Look at where the positive charge is. We want to form an alkene. And at this point, we have been mentioning a lot of times how we form alkenes. Look at one step away from where the double bond, the positive charge is. You can look at this carbon here. You can also look at this carbon here. So you are going to be able to grab the hydrogen from those. But I can't grab the hydrogen from this carbon here, because if I grab the hydrogen here, it means that the double bond that I'm going to be able to form will be here. And we don't want to form a compound which has got double bond just next like that, because that is highly unstable. So instead, the hydrogen that we grab will always be on here. So this chlorine will come and grab this hydrogen. That will break off this bond and form a double bond here. That is very small, you can see. Maybe I use a different color. So we are breaking off this double bond. I mean the bond with the chlorine. It's coming here. So we are reforming our bond here. And then we still have our group at that point. Now, sorry, this chlorine isn't there. I just wrote it. I should have been thinking of something else. There's no chlorine there. So remember, this chlorine has grabbed the hydrogen. So in the process, we are also forming hydrochloric acid. So this is a mechanism. And if you remember Friedel-Crafts acylation, we said you always add the compound that we have. We had Ara that bonded to oxygen and then Cl. Simply remove Cl and then at this end connect to your ring, and that's what we did. Our Ara group in this case was a methyl here. Is this okay? Is this okay? Okay. Please be free at any point if you are not good to pause me, because it will be you can't say no. I'll go through if there's a chance to understand just now. So be very free. So that is the production of F, and that was by Friedel-Crafts acylation. So now I want to form the other one here. What will be this mechanism? Anyone? Look at the reactants. What are we? What by what mechanism are we going to form that? Nitration. Thank you very much. So always the thing that is on top is actually what will be added to our compound. So, but we are not adding the nitric oxide. From here we just remove the nitrogen dioxide or nitric oxide. We are not adding the nit- nitric acid. We'll just remove a nitric oxide. So first thing first, remember for all these steps, your reactant to first react. So I want to write it like so. H bonded to a nitrogen and then O3. Okay, this is how I want to write my nitric oxide. And this one is reacting with sulfuric acid, and I want to write sulfuric acid like this. So in the first step, what happens that this nitrogen acts as a good nucleophile. Let me write this molecule properly so that we see how the structure is going to be. Nitric oxide itself, we have got a nitrogen, and this nitrogen is bonded to oxygen by a double bond, and then it's bonded to another oxygen, okay, like that. And then now it's going to have the hydrogen here is bonded to another oxygen as OH, like this. This is what I wanted to leave out. If you don't want to write it like this, you have got a choice to write it in an easy way. And you can just write H bonded to O and then NO2. You can also write like this because this is the NO2 here. But this structure is going to be necessary at the end other than this other one which I've written down. Always remember the oxygen attacks to remove the proton, this bond breaks. And the aim is, remember, we want to form NO2 because it's NO2 that we are attaching to our compound in nitration. But we could have easily done it by just removing this hydroxide, but hydroxide is a bad leaving group. We want to convert it to a good leaving group. So that's the aim of this process. So we're going to do this. And then we have formed oxygen bonded to two hydrogens. And this is having a positive charge. And then in the next step, what will happen is that this will leave. Okay, that will leave, and then we are going to form our NO2, and this thing is going to be positively charged. Remember, always we form something positively charged. This was at step 2, so that what is positively charged in step 3 will be attacked by our ring. So the ring will come in. Look at this. I'll now write this structure like this. This one has a positive charge. Okay. So this will come and grab this, and what we are going to form, double bond here, a double bond here. The N has bonded. I'll just write it like this. But then there's a positive charge at this point. Don't forget, this thing is going to be stabilized by resonance. So write the two resonance structures. Just move the double bond, the first double bond up to here, and then you're going to be able to move the next double bond up to here. Don't forget, unless you don't want to get all the 12 marks. So in the next step, that is now going to be step 4. We have a double bond here, double bond here. Our NO, there's a positive charge here. So now come and remove this hydrogen. But then what we are going to use, the same thing that we had formed at this step, is what we are going to be able to use. Okay, which is the OSO3. I just forgot to write the product minus. So that will be released OSO3H. This one has a minus. So I'm going to come and remove this proton. That will break this double bond to come and form a double bond here. Not a double bond. We are not breaking a double bond, but we are breaking a bond with a hydrogen. And then we have our NO2 here. Then we have reformed our double bond here. So that is going to be our product. Is that okay? Okay. We have got this one now. This is an interesting question. It's not there in the tutorial sheet, but you need to apply information. 2-methyl naphthalene can be synthesized from toluene through the following sequence of reactions. Write the structure of each intermediate. So just starting from the first one, if you just fail to write the structure for toluene, you are going to continue going on and on and on, and you might not just be able to write the final product. But then something can help you here. Something can help you. You just look at your final product. I know this wasn't easy. Yeah, it wasn't. But then you look at your final product, you have got 2 rings, and toluene is actually 1 ring. But look at the reactants you have. You have got aluminum. What's that? Aluminum chloride, something like that. You're also using water. And then you have got this ring on top. This is okay. So let's go on. How are we going to start? I'm going to start with the structure that has been given on top there. Oxygen, bonded double bond to oxygen, and then another bond to oxygen. Okay, like that. Our toluene is a benzene ring. That is a benzene ring which has got a methyl somewhere, like that. So in this mechanism, it will be a mechanism the same way with the previous ones that we have done. So what will be happening is that there's going to be attachment. So there's supposed to be alternating bonds inside here. Double bond here, double bond here, and a double bond here. So what will happen is that we actually break this double bond to be able to attack this compound. So every time you see a compound, like you have got a compound oxygen, sometimes you see it like this. It will be the same mechanism as long as you have got oxygen on the middle, double bonded to other oxygens. It doesn't matter whether it's in a ring or it is just a straight molecule. It will go by the same mechanism. So what you are going to see is that this double bond will be able to attack this your group. But then because of the aluminum chlorides that you are able to see here, let's write a structure that you are going to be able to see. You can see they've also given you the formula, at least C11H12O3. The structure that you should be able to form should have 3 oxygens, should have 11 carbons. So even if you didn't know the structure for toluene, just count. This one they've given has got 1 carbon, 2 carbons, 3 carbons, 4 carbons. And I want to reach to 11. It means that the next one I should have should be 11. I mean 7 carbons. So you predict, okay, I know it should be something benzene because these are benzene reactions. So that's how you predict something that you don't know. The product that you are going to be able to form on the first reaction. We are going to still have our ring here, but then we are going to get this our compound and be able to attach it here. So we'll start attaching it. This one oxygen that you can see here, the bond is going to break. Just know that happens. The bond here gets to break. Take note of that. When that bond breaks, you are going to have one. Look at this. You are going to have one oxygen at the end of your chain. That still has a double bond. And that's the one that we are going to use to attach to our benzene ring. Okay, every time you have got this reactant, the bond that you have is going to be able to break. And then at the end that it has broken into, if it breaks here, this oxygen will remain with a negative charge. This guy will come and attach to our ring. Take note of that. Very important. So it will come here with a double bond with oxygen there. And then continue now the rest of the carbons. Let me break it at this end so that it will be easier. So this carbon, let me even number them 1, 2, 3, and 4. So number 1 is this one. So I'm remaining with how many? 4. So that will be number 2, number 3, number 4. Okay, 4 of them. Remember on the fourth one, we have got a double bond with oxygen, and then we have got the other oxygen which will have a negative charge. Now, I'm not writing a mechanism, but at the beginning, this double bond is the one which actually did attack. When it attacked, the bond here had to break to form the negative. Now remember when the double bond attacks, just like the previous mechanisms we've been talking about, there's going to be a positive charge that is going to be formed. But what will happen is that the hydrogen which will be at this point when the positive charge is formed, this oxygen that is formed here with a negative sign will be able to attack itself as a ring to be able to grab a hydrogen here because initially there was a positive charge to come in and grab this hydrogen. So at the end, you'll not form the oxygen with a negative charge. So it will be an alcohol. So this will be the first compound as the first product that you're going to be able to form. These reactions are interesting. So I'll see I can take, okay, I don't even need to take a class. Just go and watch the tutorial on aromatic hydrocarbons just to peruse through. But already we are getting ideas of how the reactions will happen, so there's no need of you worrying. Let me pause here because this is big and it's not about no, I'll do it later. We are doing it now. Is this okay? Okay. All right, sure. So the first thing first that happens that your ring will be able to attack at one end where there's a double bond with the oxygen. When that happens, the bond with the other oxygen will be able to break. So you form oxygen which is negatively charged. But when the double bond is the one which attacks, it means one carbon will be positively charged. because the double bond inside the ring will be broken. This one, this oxygen which has a negative charge, will act just like the previous mechanism that we talked about to grab the hydrogen, and then the bond breaks to form back your double bond. That's how you end up with this product. Is that okay? Okay. Let me write this from the beginning here so that we can have some space. Now at this step, look at the next thing that you are using. You can actually even count the number of atoms that you have, also including the number of hydrogens that you have, if it will balance with this formula. Okay? You can do count that and you see it will. So this is the structure A. Now we are reacting this structure A with zinc in mercury, and then I've got hydrochloric acid. Now, what should you know about this mechanism? What you need to know that every time you see zinc in mercury reacting with a ketone, it will remove the ketone function. It converts a ketone into just a linear alkane. So between this group and this group, which one is a ketone? Anyone? The one on top. Thank you very much. Yes. What functional group is this? So yes, that's correct. It's like a carboxylic acid. That's correct. So what will happen is we are going to now have this structure. The only thing that has changed is that we no longer have the double bond on top. It's not there. So this is the ring that we end up forming. Is this okay? This is our structure B. And if you look at the structure B, it had the formula with two oxygens. That is because one oxygen has gone by this same reactant. Is that okay? It's quiet. Please, if it's okay, if it's not okay, you can tell me. Okay. Now the next reactant we are using is SOCl2. This is where now we start applying different concepts. We talked about the mechanism with SOCl2. Okay, we talked about this mechanism. When you are using this reaction, maybe that when you react a carboxylic acid with SOCl2, you need to know that actually when you are reacting an alcohol with SOCl2, that alcohol is displaced and replaced by a chlorine. Alcohol displaced, replaced by a chlorine. So we still have this, but then at the end, we now have a Cl. Okay, that is the structure that we form. And if you can see the formula, there is a chlorine there. Please take note. These are just principles that we are moving with. So that is our structure C. From the structure C, what are we reacting with? We are reacting with aluminum chloride. And we know this reaction. I believe we do know this reaction. Reacting with aluminum chloride. That should be the one. If I can't. Okay, that's the one. Now, when you use this reactant, what happens is that this guy, the chlorine, will be able to attack the aluminum chloride. It's like the more the same as the one we previously talked about. When that happens, now we can be able to break that bond, and then we are going to release AlCl with a 4, and this is a minus. So meaning that the bond that we are going to remain with here is going to be negatively charged, and that is not stable, right? With that negative charge, it is not stable. So what happens is that that end which will remain negatively charged will act as a nucleophile attacking the other end of this compound that we have, and that will form a complete ring. So we form two rings which have been merged. So this is the structure that we are going to be able to form, and this is our structure D. Are we moving together so far? Okay, so we continue from structure D. Now look at the reactant that we are reacting structure D with. Sodium borohydride. We've been mentioning this. From sodium borohydride, what do we get? So we've been mentioning from sodium borohydride, we just get anhydride. That's the only thing that you get. Okay, every time you see sodium borohydride, you just get anhydride. Anhydride is a proton, negative charge. So you are going to convert, when you use sodium borohydride, you convert carbonyl groups into an alcohol functional group. Convert a carbonyl group into an alcohol functional group. So this one acts as the nucleophile and it gets to attack there, and that breaks the bond there, double bond. It goes to the carbon. And now we have got the OH functional group here. Okay? And this is going to be our structure E. If you can see, this is now one carbon, okay, one oxygen. There are 14 hydrogens, C11. That's our new structure. Then from this one, we are reacting it now with what reactant? Sulfuric acid. This one we are familiar with it. Sulfuric acid in heat. When you react alcohol with sulfuric acid in heat, what do you produce? Anyone? What do you produce? Yes, you form an alkene. So you see the way they brought this question, they combined a lot of topics in one. So just where you had the OH will no longer be there, we're going to form double bond. Okay. You also have alternating double bonds here. So this is the structure that we are going to form, and that is going to be our that will be our F. And then from F, we are reacting it with sodium. What is this? Sodium ethanoate. Oh, sorry, I've gone to something else. Let me just see what's NBS in light and carbon tetrachloride. Should be that's the F, yes. So we are reacting with NBS. Okay. Now for here you can directly see that even if you don't know what NBS is, at least you can see to your molecule they have added the Br. So you can even guess, okay, I need to add a Br. But the only problem should be, where am I going to add a Br? That will be the problem. And that one you can also have clues where you should be able to add your Br. Look at this. We are forming a double bond at that point with uh, oh, we have actually swapped our molecule. We've turned it around. We had a double bond here, double bond there, here. Okay, we had the double bond here. Now we are adding a Br in our molecule. Question is, where should we add our Br? I can tell you I have never on this topic I've not seen these reactants. But then you can just predict where you are going to be able to add your Br. I don't know how best you can do that. But look at this. How do you know where you're going to at least have an idea? Look at the chain that we had. This chain had alternating bonds, but look at how it is now. There is a double bond somewhere there, right? There's a double bond somewhere there, and where we are not supposed to have it. And by the way, if you swap it, this other benzene ring here is the one which had this methyl. But you can see we've put now our methyl this side. So this is just the arrangement of our methyls. It can change. Not the methyl, sorry, the arrangement of our double bonds. If I started writing this double bond from this end, it means that everything else is going to rotate. But I don't know how best I can tell you how you can add the Br. I guess this is where now guesswork starts to come in. This mechanism, I've not seen it on the reactions from the first topic to the last topic. So we're going to add our Br there, and then after you add your Br, you are going to introduce another bond at the end of it, or when you use the sodium ethanoate. Now, sodium ethanoate, at least you can know. I'll tell you how you can guess where to add your Br. Sodium ethanoate is like this. This is a strong nucleophile. Okay, it has got two. So even when you are making gases, you are making gases which are what? Which are chemical gases. So what this guy can come and do is that it can come and grab a proton to form a double bond. Now, every time this mechanism can move by SN1, by E1 or by E2. Remember where you have got your halogen, you grab the hydrogen one step away. You can either grab the hydrogen from here or a hydrogen from here. And I can't grab the hydrogen from here because I'm going to form something that is unstable. So definitely I'll come and grab this hydrogen from here. And this bond will break and come and form here, and that will make this thing to go. But let's say I had put this bromine at this point. It will mean that the double bond I'm going to form it here. And look at this. From the molecule that you've been given, the bond should be alternating, meaning that already that structure is wrong. So we're also looking at the last structure to direct you what you are going to be able to form. So the last structure that you are going to be able to form, now I can write it down. It has already been given. I'm just predicting how we would have written it. Would have written it like this. This would be the last structure. Okay? Would have predicted it like this. Now these bonds in here, they can shuffle because of resonance. This can come here. This can, like, just because of resonance, they can shuffle around. That's why you can see the side where you've got a methyl, that is where you've got two bonds inside. Okay? But good news, that structure is already given there. So that is how you could have predicted the products here. So what did they want us to understand here? They wanted us to understand, if you have got this reactant, what do you form from this other reactant? That was the aim of this paper, or of this question, let me say. Does this make some sense? I don't accept, it might not make the total sense because some things you are seeing them for the first time, you might not have gone through the mechanism. Trust me, I'll share with you the tutorial so that you go through the mechanisms so that you understand them. Is this okay? Yes, sure. Okay, let's look at this. This is going to be our last question here. Question 3, probably with question 4, we'll do it uh, in the next tutorial. When benzene reacts with 1-chloro 2,2 dimethylpropane, which is also known as neopentyl chloride, in the presence of aluminum chloride, The major products is 2-methyl 2-phenylbutane, not 2,2-dimethyl 1-phenylpropane. Explain this result. Okay, so look at what they are talking about. 1-chloro 2,2-dimethylpropane. It's a propane. So first we write 3 carbons. 1, 2, 3. At position number 1 we have got a chlorine. Position number 2 I've got 2 methyls. This is a compound that we are reacting. We are reacting it in the presence of ammonium chloride. They are saying we are forming, the major product is 2-methyl 2-phenyl butane. So 4 carbons. 1, 2, 3, 4. You can say at position number 2 we have got a methyl. Position number 2 we have got a phenyl. A phenyl group is this one. And not, so this is major, and not 2,2 dimethyl 1-phenylpropane. This is propane. 1, 2, 3. 2,2 dimethyl, 2 methyls here, and then a phenyl at position number 1. Okay, this is the minor. So the question is, why is it that we are forming the major product being the other one and not the other one? So remember we said, the first thing is you need to predict a mechanism, and then you'll be able to write your product. In step 1 I had already mentioned this. From the previous question we said, every time you are reacting something with the chlorine with the ammonium chloride, what happens? Let me write the chlorine this side. What is going to happen? Anyone? Yes. Okay, one of the reactants, another one is benzene. Benzene reacts with that. So chlorine is going to come and attach here. And what we are going to be able to form is going to be this. We have got chlorine bonded to aluminum with 3 chlorine. So this will be negatively charged. This bond breaks off. That's a good leaving group, right? When that bond breaks off, then we are going to have I written even the right thing? This was 1, 2, 3. So I've forgotten something here. I was supposed to bend that bond. Okay, it was supposed to be like this. So it's this bond that is breaking. So the product that we are going to have is going to be like this. There's a positive charge here. Now this thing can undergo a methanide shift. This methyl can shift and go at the end. And then what to be able to see is this. We remain with 2 methyls, this methyl and this methyl. And then at this other carbon here, we're going to have another methyl, which has come to attach. The positive charge is going to shift up to here. So because of that methanide shift, we have formed a tertiary carbocation which is more stable than a primary carbocation. Let me write this thing again because of the space here, it's making me write wrong things. I'll write it from this end. There's a positive charge here. Remember we are saying there's going to be a shift of the methyl. A methyl is going to shift from here up to here. We are remaining with this methyl and this methyl at this end, so I'll write them like this. And then we have attached a methyl at this one end, okay? And then the positive charge has moved, it has come here. This is a primary carbocation, this is a tertiary carbocation. Which one is more stable? The tertiary one. So what will happen is that now your benzene ring is going to come in. Remember what we've been doing? It acts as a nucleophile, comes and attacks here. Okay, when it attacks there, look at what you're going from. This is your benzene ring. I'm just writing the last product. From the previous reaction, you saw what the mechanism would be. When it attacks here, there's going to be a positive charge here, right? And then we'll use this same thing which was produced here to come and remove a proton, and we are going to produce hydrochloric acid. We already looked at that mechanism earlier. So we are attaching at this end. So here it says at this point we have got two methyls, and then I've got a methyl here and a ethyl. Actually, this will be the product. This will be the major product, and this is this one, simply because it is being formed from a tertiary carbocation. It will be the same. This guy, the same benzene, will come and attach here, and that will form this one, but it's going to be minor because it's formed from a primary carbocation. So those are the reasons that we give for this one.